All right, this section is an overview of both sequences and series. So now that we've covered our sequences, let's take a minute and talk about our series here. So again, we're going to write out the definition. So this is the definition given in the book because I feel like it has lots of good information for us. So here it is. Given a sequence. And my sequence here is a sub 1, comma, a sub 2, a sub 3, etc. The sum of its terms is a sub 1 plus a sub 2 plus a sub 3 plus all of that is equal to, and then here is the symbol that we're going to love. This is sigma. It's a capital letter in Greek, all right? Here, let me see for this first one that I'm drawing out that I actually do a better one. It's the summation notation, right? Oops. It's that summation notation. Like in Excel or any of that, you're doing sum, right? So this is, I'm summing this up from 1 to infinity that I'm looking at here as my a sub k, all right, is called an infinite series. And that's where we are going to be spending most of our time is with series. We're going to do a little bit of sequences, so we got an intro to it today. We're going to do it in the next section with sequences, and then the whole rest of the chapter is going to be spent on series, all right? But you can see the connection. A series is simply summing up all of the terms in my sequence. So here it is. The sequence of partial sums. This is a big deal right here. The sequence of partial sums is denoted by, that's a squiggly bracket, S sub n. Oh my, they're getting worse. They were getting better for a little bit. Now it's going back downhill. Associated with this series has the terms. Okay, now I'm going to scoot this up a little bit here. S sub 1 is equal to a sub 1. S sub 2 is a sub 1 plus a sub 2. That's what makes it a partial sum. S sub 3 is 1 plus 2 plus 3, etc. S sub n is a sub 1 plus a sub 2 plus a sub 3 plus all of them all the way up to the nth term that you specifically want. And that is denoted here by k going from 1 to n of a sub k for n is equal to 1, 2, 3, etc. All right? So a partial sum is just the part that you're looking for there. Okay, so here's the real deal Holyfield. This is where we're coming at it. So all of this information is culminating into this. If the sequence of partial sums denoted by S sub n, has a limit L, the infinite series, infinite series converges to that limit. Oh, there's that word again. And we write that the sum here of k going from 1 to infinity of a sub k equals the limit as n approaches infinity of the series k going from 1 to n of a sub k, which is equal to the limit as n approaches infinity of s sub n, which equals L, because this is representing S sub n, right? Okay, so one more statement, and then we're going to bring this home. We're going to talk it all out. If the sequence of partial sums diverges, the infinite series also diverges. Okay? Okay. All right. I'm going to squeeze this in. We got a nice full page of information here. So let's talk it out. Here it is. Given this sequence, all right, when you add up the terms of a sequence, you get a series. That is what's happening right now. When you add up the terms of a sequence, you get a series, and that's what a series is. All right. Now, if I want to find the value of my series, that's the kicker, isn't it? Whenever I want to find the value of my series, I am looking for this partial sums, and that is a pattern. That's where we're going to be looking at this. Your sequence of partial sums is what we're going to be finding, and that is going to be a pattern. And we're going to get that pattern by looking at the different terms, and when we add those up, what do we get? Notice here, S sub n is equal to this. Oh, check it out. Have you seen that? Again, right here. So this is my S sub n, and that's where we take that limit. All right. This is the mathy way to say it. Here's the moral of this story. When you come up with this pattern, we're going to go straight to here. Find your pattern. When you find this pattern, we're going to go straight to here and take its limit. All right? If L, oh, no, wrong thing. If there is an actual value L, then it converges, right? If not, then it diverges. If it goes to infinity or doesn't have a pattern or whatever that is. If I don't come, not just a pattern, but doesn't come up with a specific number, just like in our sequences, then it diverges, all right? And if my partial sums diverge, so does the series. Okay? Okay, well, you know we're going to do examples. Sit tight.